Scientists often need to calculate the energy changes that occur between two different substances that are combined together in an isolated system. When two substances at different temperatures are added together, one substance will lose energy as the other substance gains. The amount of energy lost from one substance is always the same as the amount of energy gained by another substance in an isolated system. The sign in front of the amount lost will be negative, and the sign in front of the amount gained will be a positive number. Here we have a sample heat exchange problem. If 75 grams of iron at 95 degrees Celsius is added to a 100 gram sample of water at 10 degrees Celsius, what will the final temperature be? It helps to draw a picture and write a plus next to the sample absorbing energy and a negative next to the substance losing energy. We're going to write an equation to represent the heat loss as equal to the heat gained. We'll need the specific heat values for iron and water. Let's first write an equation that tells us about the heat loss occurring with our iron. We'll represent that with minus Q loss. That's iron losing heat. That heat is getting transferred to the water. So we'll put a minus sign. And we're not dealing with heat of fusion, and we're not dealing with heat of vaporization for iron. We're just using mc delta T, the mass of iron that we have, multiplied by the heat capacity of iron, multiplied by the change in temperature, the temperature final minus temperature initial. We know some of that information. You know we're dealing with 75 grams of iron. We know the heat capacity of iron. Final temperature is something that we don't know, but we know the initial temperature, 95 degrees Celsius. So that's what we know about iron losing heat. We also know some information about the water that's gaining heat. First, we know that it's going to be equal to the heat that's lost. This is water gaining heat. That is the mass of water times the heat capacity of water times the change in temperature of the water. So this side we're just dealing with what we know about the water. The mass of the water, 100 grams. Heat capacity of water, 4.184 joules per gram degrees Celsius. And then we have our change in temperature. Temperature final is going to be the same temperature final over here. They come to an equilibrium. They come to a single temperature. This will all be at the same temperature. Initially, our water was at 10 degrees Celsius. Now we have some serious math to do. I'm going to work on simplifying this. 75 times our heat capacity, this is just going to be a number. That number is going to be multiplied by delta T. We're going to have another number over here, again multiplied by delta T. So I'm just going to work on simplifying. step, distributing the 33.3 to the TF and to our initial temperature, which will come up with just a number. Going to distribute the negative sign there. Negative times a negative is positive. So I could see that this number in front of TF is larger. I'm going to add 33.3 TF to both sides. Then I will take this number here, add it to both sides. Okay. We'll do that one step at a time. So we're adding that 4184 number to both sides. The end is near. Now we just have to divide each side by 451.7 to get TF by itself. So we'll take this number, divide by 451.7. Okay, so we have a final temperature from our calculations. Now we have to think about if this makes sense. Do we have a number that's greater than 10 degrees Celsius? Because we know that water is gaining heat. We also know the temperature must be below 95 degrees Celsius because iron is giving up its heat. We have to come to some sort of middle ground, and it should be a lot closer to 10 degrees Celsius. Water has a huge heat capacity, 4.184 joules per gram degree C, versus iron's very small heat capacity. So water can take in a lot of heat, and its temperature won't change drastically. So this makes sense, and this is the correct answer.